So we're going to be doing a question on parallel and series capacitors. Okay, so this is a bit of a tricky question and a little lengthy as well. So we have to find the charge on each of the capacitor and the potential difference across each of them. Okay, so first thing I'm going to do is I'm going to find the total capacitance. So this is going to be C1, C2, C3, and C4. So let's find the total resistance of C2 and 3. Since they're in series, it's going to be 1 over 40 plus 1 over 40 to the power minus 1, which is going to be 20 microfarads. So then I can draw it like this. Okay. This is going to be 20 microfarads. 20 microfarads. And this is 10 microfarads. So first thing we have done here. Okay. Now the second thing I'm going to do is I'm going to find the total capacitance of both of these capacitors here. They're in parallel, so I'm just going to add them up. So capacitance of 2, 3, and 4 is going to be 20 plus 20, so 40 microfarads. So we're going to have our circuit looking like this now, where we have two capacitors, 10 microfarads and 40 microfarads. This is C1, this is C2, 3, and 4. And thirdly, we're going to add the capacitance of both of these. They're in series, so it's going to be C1, 2, 3, 4 is equals to 1 over 10 plus 1 over 40 to the power minus 1. That's going to give me 8 microfarads. So we have 8 microfarads. And yeah, that's going to be our final thing we're going to do. And now we can work step by step. I'm going to give a little bit of space here. Okay, so we've got here our 20 volt battery. Okay, now we can find the charge that's stored on this capacitor. So Q is equals to CV. So 8 times 10 to the raised power of minus 6 times 20 divided by 1 times 10 to the raised power of minus 6. That is going to give me 160 microcoulomb. That's the answer. So the charge stored on this capacitor is going to be 160 microcoulomb. I hope that's clear. Now, let's come back. Now we're going to reverse back. Okay, we're going to reverse back. Okay, so again, we have 20 volts here. And remember the charge, if two capacitors are in series, the charge that both of them get will be the same. So this is going to be 160 microcoulomb, 160 microcoulomb. Okay, so now what I want to do is I want to find the potential difference. Because remember, if you watch the previous video where we derived the equations of the equivalent capacitance in series and in parallel, we said that the potential difference will be divided. So it'll be split between both of these. Okay, so we have to find out how much one gets. Okay, so let's do for C1 first. Second, let's call this V1, V2, 3, and 4. So let's find V1 is equals to Q1 over C1, and V2, 3, 4 is equals to Q2, 3, 4 over C2, 3, 4. So I'm just going to quickly plug in the values into all of that and get the answer. So for V1, I'm getting 16 volts, and for V2, 3, 4, I'm getting 4 volts. So write that down, 16 volts and 4 volts. Okay, so let's just put this information here. So it's going to be 160 microcoulomb and 16 volts. Okay, so we have got the first set of values for our capacitor C1. Okay, now we gotta go back to step 1. We gotta fill the information in there. Okay, so we've got here now capacitor 4 here, and then this is capacitor 4, C4 here, and this is C2, 3. Okay, now we know that the potential difference here is going to be 4 volts. Okay, which means, remember in parallel, potential difference is the same. So 4 volts here and 4 volts here as well. Okay, so let me just write that down. It's going to be 4 volts here, and it's going to be 4 volts here as well. Okay, so we've got another piece of information. So C4, the potential difference across that will be 4 volts across this one. We can also find the charge for C4, which is going to be Q4. So Q4 is equal to C4 times V4. So that's going to be 20 times 10 to the raised power of minus 6 times 4. Now I'm also going to divide it by 1 times 10 to the raised power of minus 6, so I get it in microcoulomb. So I'm getting 80 microcoulomb. Okay, so it's going to get 80 microcoulomb. Okay, now let's talk about the potential difference here. So we've got 4 volts here, and since capacitor 2 and 3, they both have the same capacitance, so they're going to share that 4 volts equally. So it's going to be split 2 volts here and 2 volts here. Okay, now remember the charge across the capacitor 2, 3, 4, when we combine their capacitance 2, 3, 4 of the capacitor, our charge Q234 was equals to 160 microcoulomb. Okay, remember that? Out of that 160, basically the 160 will be split between these three. So out of the 160, 80 is being given to C4. So 80 is being given to C4. So that's minus 80 from here. We're going to get 80 microcoulomb left. And the rest of the 80 is going to go this way. Okay, it's going to be split. So 80-80 split will happen. Okay, it's also because, remember, the capacitance here, the effective capacitance is 20 microfarads and 20, so it's going to split evenly. So 80 here and then 80 here, and the total will be 160. Okay, so I hope that is clear. And that 80 that's coming here to capacitor 2 and 3 will be split again. It'll be split evenly. Okay, so we're going to have 40 microcoulomb here and 40 microcoulomb here. Let me change this as well. Why did I write 4 here? It should be 2 volts. Okay. Right, so we've got all the values now. 160 microcoulomb, 16 volts, 2 volts, 2 volts, that's 4 volts, 40 microcoulomb, that's 80 microcoulomb, 4 volts here, 80 microcoulomb here. Pretty long question, I know. But yeah, that's the answer to this question. I did it stepwise, bit complicated. You can actually pause the video or watch the video again, and maybe try the question out yourself as well. So I'm just showing you the entire process, how we did that. And if you have any doubt, let me know. Again, be very strong with your energy conservation and charge conservation, basically Kirchhoff's voltage and current law. You can apply that here as well, and that's what I've done here. And just be strong on that AS electricity chapter, then you'll excel very well in this chapter as well. Okay, that's all. How are capacitors even storing charge here? So we've got capacitors in series, and you might ask, how are they even able to store charge? This upper plate over here of the capacitor C1 is going to be positive. This lower plate of C2 is going to be negative. But what about these plates over here? Right, this is the lower plate of C1 and upper plate of C2. How are they going to gain a polarity? How are they going to be positive and negative? They're not connected to the battery. And the way this works is we're going to have a negative charge developing here because the negative charges are going to be attracted to the positive charges on the upper plate of C1. And then we're going to have a positive charge developing here because the positive charge will move down as they're going to be attracted to this negative charge here. Okay, because of the negative charge is stored on the lower plate of C2. Okay, so basically this is going to be negative because charges are going to be attracted to the positive plate, and then this is going to be positive because charges will be attracted to the negative plate over here. So they're going to develop the charge like that on both of those capacitors, even though this area over here is not connected to the cell or battery at all. So that's kind of a bit of a unique case, because when you talk about parallel, it makes sense. Okay, that's something that we have studied before. But with series, it's a bit more unique. Okay, so I just wanted to point that out. And that's all.